As the final step in our calculation, let's work out if this pressure is actually sufficient to produce a white dwarf like Sirius B. So we've calculated the pressure we need. We've also calculated in an earlier video the pressure in the middle of a white dwarf, and we found that the pressure we need in the middle of a white dwarf of uniform density is 2/3 pi g density squared times the radius of the white dwarf squared. Now we also know that the density is just the mass of the white dwarf divided by the volume, which is for a sphere 4/3 pi r white dwarf cubed. So what we can do is substitute this into here. That gets us the pressure in the middle of a white dwarf and set it equal to the quantum mechanical pressure. And from that we can deduce what the radius of the white dwarf actually is. And I'll leave that as an exercise for you. It's fairly straightforward, though a bit algebraically complicated. But what you get is that the radius of a white dwarf is given by and there you have it. And if you plug numbers into this, you come out with an answer of about 3,000 kilometers, which is about half the real size, about 6,000 kilometers as we derived earlier. So considering all the approximations that have gone in here, that's a pretty good job. So you can see that using quantum mechanics, you actually can explain how white dwarfs can sustain themselves going from fundamental principles, which is pretty amazing, this linking of the very small to the very large. There are also a few more puzzling things that we'll come back to. For example, you can see that the radius of the white dwarf goes down as the mass goes up. If you make the mass bigger, it's on the bottom here, so the white dwarf actually gets smaller. And that's going to have really important consequences later.